All right, this is day 24. We are talking more about confidence intervals. This time we're talking about confidence intervals for quantitative variables, whereas last time we were working with only categorical variables. All right, so I've had this slide up at the start for the past 3 videos or so. The reason I keep coming back to it is because it is so important to make this distinction between the population's parameters and the sample's statistics. So last week when we were talking about probability, we were assuming that we understand what the population is doing. We're assuming that we understand the big picture, and we ask, all right, if we take a sample, if we take a subset of that, and look at something like the mean or the proportion, what do we expect to get? All right. Inference, on the other hand, is going the other direction. We are taking some sample from some unknown population and saying, well, in this sample, I saw that, 6 out of 10 M&Ms were green. Maybe that is indicating something about the population. So inference is saying, what can we say about the total population, like the general population of M&Ms, given the little bit of information that we have? And again, last time we talked about categorical variables, which we can keep track of by paying attention to the proportion or the percentage of a population that falls under one category or the other. So this P or P hat number encodes really all of the important information about the population or sample. With quantitative variables, things get a little bit trickier. When it comes to categorical variables, we really only need one number to basically tell the whole story. Here we're concerned with, how many M&Ms are green versus not. And there's a few ways we have of presenting the data. We could use a pie chart or a bar chart, or just say the number, say the percentage that matters. And there's no ambiguity. Like, once we have this bit of information, that tells the whole story. That's not quite true for quantitative variables. When it comes to quantitative variables, the data just gets more complex. By specifying a mean, we don't necessarily tell the whole story. We can have multiple distributions that all have the same mean that are, very much different distributions. We could also specify the standard deviation. This is going to give us more information about what the distribution looks like. But again, we could have drastically different looking distributions that have the same data, have the same mean and the same standard deviation. The reason I bring this up is just to point out that quantitative variables are inherently more complex, but thanks to the intermediate value theorem, which we'll talk about in just a moment, a lot of the same logic that we applied last time with categorical variables is still going to apply for quantitative variables. All right, since Halloween's coming up, let's stick with our candy theme. So earlier we were asking how many M&Ms are green, and we were paying attention to the proportion or the percentage of M&Ms that were green. Now let's talk about Twizzlers, also known as red vines, and let's focus on how long they are. So now we have a quantitative variable, which is the length of a given red vine. Let's say that we want to know what the average length of a red vine or a Twizzler is for every one of them coming out of a factory. So the population is going to be the entire collection of Twizzlers coming from this particular factory, and we want to know a particular component about it. We want to know the length, the average length. Before we do that, we need to think about what we expect the sample to look like in the first place. And this is going to depend on what the overall population is doing, as in what the entire distribution looks like. All right, let's look at a hypothetical. Let's say that our population, let's say that the length of Twizzlers coming out of this factory follows this nice normal distribution. All right, and then our x-axis is a measure of length. And then so to estimate what the average is, so what we're focusing on is what the average length of a Twizzler is, we can take a sample. So let's take a sample of a size 5. And look, we got these 5 pieces, and the average was down here, which is pretty close, maybe a little bit off, but not terribly far off. Let's clear that, and if we took a different sample, this one happens to be even lower. So the question is, what does a typical sample's average look like? And this gets a little bit confusing because we have multiple distributions floating around. We have multiple means. There's this original picture, which is representing what the population is doing, and it has its own mean and standard deviation. But then there's also a distribution representing how likely it is for a certain sample's average to be a certain value. To see that, let's take some more samples. So if I take another sample, we can record its average, and another sample, we can record that average, and I can repeat this process, taking more and more samples. So each time I pick out, my sample size is 5, each time I pick out 5 pieces and then record what the average is. And if I keep doing this, so incrementing by 5 so far, let's add another 10,000. If I keep doing this, we can see another distribution. So this is the probability distribution for the sample mean. Up here we have our original distribution. This is what the population looks like. We take a sample, record what the mean of that sample is, and that's going to be something random depending on which 5 we chose. But it's going to be more likely to be in the middle than it is out on the sides. When we were talking about proportions, we had a population information, so some percentage of the population is a green M&M. And when we take a sample, we expect that proportion to be, roughly that actual population's proportion, but give or take some amount. There's a whole probability distribution of what those proportions are. The same thing is happening here. And like last time, we're going to use information about the sample to say something about what the population's mean looks like. All we care about is what the average length of a Twizzler is. Before we jump into how we're going to do that, let's think about what happens if our distribution looks different. So if we have maybe a skewed distribution, or something like a uniform distribution, or even something particularly crazy. So let's do something that looks particularly unusual, right? So this is a very messy distribution. It's some sort of weird trimodal thing. Now, let's do this same process. Let's take a sample, so we're sticking with a sample size of 5, and we can imagine, all right, what do we expect the average of that sample to look like? Well, if I take a particular sample, it's somewhat scattered values, but the result is still something relatively in the middle. If I take some more samples, I'm going to see more results that, again, are most commonly in the middle. So if I keep doing this, if I take more and more of these samples, we can see how the distribution of the sample means develops. So again, in blue we have the averages of the samples. So each piece is the average of a sample. And if I keep going with this, we end up again with a normal distribution. So this is surprising, at least to me. And this is what the central limit theorem says, that no matter what our original distribution looks like, so we have some really messy distribution to start with, when we do this process, when we take samples and when all we record is the average of those samples, then there's going to be some variation there, but that variation itself is also going to be normal, which I think is just kind of crazy that we started with this original distribution that's all messy, and we end up getting something familiar. All right, so the central limit theorem says that the probability distribution for the sample means, this exact process we've been talking about, is going to be a normal probability distribution. Well, then the question is, all right, how do you know which normal distribution it is? How do you know the mean and the standard deviation of this distribution? So the mean of this distribution, or the expected value of the mean of a sample, is, well, just the mean of the population. Whatever the average of the population is, we expect that if we take a sample and take the average of that sample, on average, these samples are going to have averages that are the same value. The standard deviation of this normal probability distribution is going to depend on the standard deviation of our original population, as well as on the sample size. So this is going to end up being sigma over the square root of n, where sigma is the standard deviation of the population. All right, so if we happen to know the population information, if we happen to know what the mean and the standard deviation of the whole picture, if we knew what these values are, then we can simulate what we expect the sample's averages to be. This is what the computer program was doing that I showed a moment ago. The distribution for this is just completely determined by these values. So again, this is what happens if we understand the rules of the game and are imagining what a single sample looks like. Inference is going the other way. So let's take a sample. Let's say that we take a sample and we get a certain average length of Twizzler, and the standard deviation of the Twizzlers that we measured was a certain number. How do we take that information and say something about what we think the average Twizzler length is for all Twizzlers coming out of a certain factory? When we talked about proportions, we said that the standard error was an estimate for the standard deviation. And we estimated that with our best guess as to what the actual population's proportion was, which was the sample information. We're going to do that same type of thing here. So our best guess for the mean of the population is our mean of the sample, and our best guess for the standard deviation of the population is the standard deviation of the sample. So we'll use the same notation we've used before. We're going to call this standard error now, where the standard error for this distribution is our estimation for the standard deviation of the population over the square root of n. Last time we found confidence intervals for proportions. What we're really after is what the population proportion is, and our best guess for that value is the sample that we see. It's the sample plus or minus some margin of error. And the margin of error is dictated by two things: by the z star, the critical value, which comes from how confident we want to be, which confidence level we choose, and it also comes from the standard error. Now, the standard error is the estimate, as our best guess, for what the standard deviation should be. So we worked out that the standard deviation for this sample proportion should be the square root of p times q over n. We don't actually know p and q, so we're going to estimate those things based off of what our sample was. That estimation takes the form of replacing p and q with the samples that we see. So then we get this thing that we call the standard error, which is the estimate for the standard deviation. So then we get this final formula for the confidence interval for proportions. We're going to do basically the same thing for means. What we're interested in is the population parameter, or the average, the mean of the total population. Again, our best guess for that is what we see in the sample. The margin of error, the plus or minus, is going to be some term times the standard error. Again, we can find the standard deviation of what we expect this sample average to look like. We said that that is sigma, the standard deviation of the population, over the square root of n. Since we don't know mu or sigma, we have to estimate this. And x bar is usually a pretty good estimate for what mu is. However, s, or the standard deviation of our sample, is not necessarily a good estimate for what the standard deviation of the population looks like. So while we do say that the standard error, or our best guess for what this standard deviation should be, is s over square root of n. If we just left things as is, we're actually going to be systematically estimating things incorrectly. And this stems from the fact that s isn't a great approximation of sigma. And this effect is worse with the smaller the sample size you have. For large values of n, this actually works pretty well. However, because for small values of n it's not great, and it's easiest just to have a consistent system, we're going to change the model a little bit. Rather than using our normal model, which is indicated by a z star here, we're going to use what's called student's t model. So here we have our usual normal distribution in this dotted line, and student's t model is represented by this solid line. So these should look very similar, but a main difference has to do with the tails. So the tails for student's t model are wider than they are in the normal model. And this is accounting for higher variability when we have smaller sample sizes. So student's t model is actually a whole family of curves. There's a whole bunch of distributions that all look very much like this, but are dependent on the sample size that we're talking about. As we get to larger and larger sample sizes, the student t model for those are going to become closer and closer to that of the normal model. This is actually about as different as it gets. The dotted line here is student's t model for, I believe, n equals 2, so about as different as it gets, but we can still see that there's a fairly substantial difference. All right, so again, the reason we're talking about this is because s is not a great estimate for sigma. So to address this difference, we are not going to be using our normal distribution. We're not going to be using this equation. Instead, we'll be using basically the same equation, but with t star as our critical value. It's important to keep in mind that this t star value is going to depend on what the sample size is. For large sample sizes, it's going to look very similar to the z stars, but for smaller sample sizes, it'll be more different. All right, let's finally work through our Twizzlers example. Let's say that I want the 90% confidence interval for the length of the Twizzlers. So I want to know what our best guess for the length of Twizzlers coming out of this factory is, where the sample that I take, I'm measuring 30 Twizzlers. In that sample, the average length was 8.1 inches, and the standard deviation of that sample was 0.1 inches. Well, the confidence interval is our best guess for the population's average length. Well, our best guess is still 8.1 inches, give or take some amount. So give or take our t star critical value times the standard error of this sample. All right, so what's this t star number? Well, we can look this up. The only confusing part is that rather than being indexed by the sample size, they're indexed by the degrees of freedom. So degrees of freedom is going to be n minus 1. It's always going to be one less than the sample size. And this is important when we're working with multiple variables, multi-factor stuff that we probably won't get to in this class. For our purposes, this is mostly just sort of an inconvenience. We have to translate from the sample size to the degrees of freedom. But for the 90% confidence level, t star, or the 29 degrees of freedom version of t star, I believe is 1.699. So anyway, once we have this value, we can just plug it in. And then all we have left to do is find the standard error. Well, the standard error is just our sample standard deviation over the square root of n. We do leave this as n. We don't mess with any degrees of freedom stuff for this. That's only for determining our t star. And then we just want to solve for this. All right, so if we crunch the numbers, we should see that our interval, our confidence interval, is the range between 8.002 and 8.198. So these are the values that we are 90% confident contain this actual population number we're interested in, the actual average Twizzler length for this factory. Okay, there were a few extra hoops to jump through to finally get to something that looks like an equation, but now that we're here, actually finding this is very similar to the examples we did last time.